Hello everyone, this is Professor Ng Chi Kun from UNIMAS. In this video, I'm going to give you an example on how to do the fracture design for a beam with durability and serviceability considerations in reinforced concrete design. So the question is that a simply supported beam with an effective span of 7.5 meter has to carry a uniformly distributed permanent action of 10 kN per meter length on top of its self-weight and a uniformly distributed variable action of 30 kN per meter length. The beam has a rectangular section with width equals to 400 mm and height equals to 600 mm as shown in the figure below. The beam is inside a building with moderate humidity and the design working life is 50 years. Fire resistance requirement is 1 hour. Tag concrete characteristic strength as 30 megapascal. Reinforcing steel characteristic strength as 500 Newton per square millimeter and unit weight of concrete as 25 kilonewton per cubic meter for reinforced concrete. And then take main tension reinforcement diameter as 25 mm with separated bars, and then main compression reinforcement as 12 mm if any is required, and link diameter of 8 mm. So the beam that we're going to design looks like this. It's a simply supported beam, with the main tension reinforcement at the bottom to withstand positive bending moment, and then we will have compression reinforcement or hanger bars on top, if we do not need any compression reinforcement. So either this is compression reinforcement or we call it hanger bars if we only need tension reinforcement in the design. And then for the cross section we have 400 mm width and 600 mm height. Then after that we have to calculate what is the effective depth of the tension reinforcement D. So this is the calculation sheet that we use for reinforced concrete design. On the top left hand corner you have characteristic strength of concrete and also characteristic strength of reinforcing steel. And then you have the department that is doing the design, and then the designer, and then the checker. Alright, and then on the left here we have one column which is the reference to Eurocode 2, and then the middle column we have the calculations, and then on the right hand column we have output. So first of all, let us look at the first consideration that we do. So from table 4.1 of Eurocode 2, we want to determine the exposure class. So for this particular beam design, where it's moderate humidity for indoor beam, then the exposure class is XC3, as in accordance with table 4.1 in Eurocode 2. And then from table E1N in Eurocode 2, for exposure class of XC3, the indicative strength class is C30/37. So if we use this minimum concrete strength class, then our structural class is S4. And then we go to table 4.3N to determine the structural class increase or decrease. So for our beam we have exposure class XC3, and then we go through row by row in the downward manner to determine whether there is any change in structural class S4. So we are designing the beam to design life of 50 years, so we are not designing for design working life for 100 years. So there is no increase in structural class, so it still remains as S4. after considering the first row. And then for the concrete strength class, okay, we are not using any concrete strength class more than C35/45. So the structure class remain as S4. And then for member with slab geometry, we are designing a beam, so it's not a slab. So there is no reduction in the structural class. So the structural class remain as S4. For the fourth consideration is on the special quality control of the concrete production ensured. So in the question, there is nothing mentioned about special quality control of the concrete production. So we do not reduce the class by 1. So the structure class still remain as S4. So after going through table 4.3n, there is no increase or reduction in structure class. So the structure class remain as S4. And then from table 4.2 of Eurocode 2, for XC3 and structure class S4, then the C mean DUR is 25 mm. So based on C mean B and C mean DUR of 25 mm, then C mean is equals to 25 mm because they are the same. And then based on clause 4.4.1.3 in bracket 1p of Eurocode 2, then delta C deviation is 10 mm. Okay, there is no mention about quality control in the construction process. So meaning that delta C deviation is 10 mm. So the nominal concrete cover C norm is equals to 25 plus 10 mm, so it's 35 mm. And then for fire resistance of 1 hour, we refer to Eurocode 2 Part 1-2 Table 5.5. So in our design, we are using the width of 400 mm. So for width of 400 mm for R60, which is 1 hour fire resistance, you don't have a B minimum of 400 mm. The maximum is 300 mm. Okay, so the 400 mm is more than 300 mm. So meaning that we can use the minimum value of axis distance A equals to 25 mm under this column here. Okay, and then if you read the notes here, okay, SD is the distance to the side of beam for the corner bars or tendon or wire of beams with only one layer of reinforcement. For values of B mean greater than that given in column 4, there is no increase in axis distance ASD. So from R60 here at column 4, the minimum dimension is 200 mm. But the dimension of our beam is 400 mm, which is more than 200 mm under column 4 here. Okay, so in this case, alpha SD does not need to consider additional 10 mm. So in our design for this particular example here, we do not need to increase the axis distance for ASD. Therefore, the axis distance is 25 mm as we have got from B minimum of 300 mm, and then for B minimum greater than 200 mm, there is no increase in the axis distance for corner bars of single layer. So we can substitute A or ASD, okay, and then it should be smaller or equal to C nominal plus the link diameter plus the band bar diameter over 2. So in this case, C norm is calculated as greater or equals to 4.5 mm. So comparing this to the C norm just now, which is 35 mm, so we need to use C norm as 35 mm. After we have got that the nominal cover is 35 mm, then we can start calculating the effective depth of the tension reinforcement as well as for the compression reinforcement. So let's look at this illustration here for beam cross section. So first of all, we would like to determine the effective depth of the tension reinforcement. So this is denoted by D. Yeah? Okay, so from here we have D is equals to H minus of the nominal cover minus of diameter of link minus of half diameter of the member. Okay, if you have only one layer of members there. Okay, so in this case H is 600 mm, C nominal is 35 mm, diameter of link is 8 mm, and the member is 25 mm. Okay, so meaning that we have H minus of this amount, okay, which is equals to this whole amount here that we minus off from H. So we get D equals to 544 mm. So the output, we put it on the right hand column. And then for D prime, so D prime is the nominal cover C norm plus the link diameter plus half of the bar diameter. Okay, so we assume that we are using 12 mm compression bar. So we have C norm plus diameter of link plus half diameter of the compression bar. So it's 49 mm. So we put D prime output on the right column there. After that, we want to calculate the self-weight of beam. So if you have a beam of cross section P times H times L, okay, so the volume of the beam is B times H times L, yeah? Okay, and then the weight is the density times volume. Okay, so in this case is the density times B times H times L. Okay, but in design we want the weight per meter length. Okay, small letter W. So we have gamma times B times H times L divided by L again. So L is cancelled off. So finally we have W equals to the density times B times H, which is given in this calculation there. Therefore, we have self-weight of beam equals to 6 kN per meter length. Then the design action will be the self-weight of the beam plus additional permanent action, okay, multiplied by the partial safety factor at ultimate limit state for permanent action plus the partial safety factor for variable action multiplied by the variable action. So total design action we have 66.6 kN per meter length. So we put the total design action on the beam and then analyze for the support reactions and then draw the shear force diagram And the bending moment diagram, so we have maximum shear force at the supports of 249.8 kilonewton, and then the maximum positive moment at the midspan of the beam of 468.3 kilonewton meter. For the main reinforcement design, we use K balance of 0.167. So the first step of design is to calculate value of K, which is M over FCK BD square. So the moment M is 468.3 kilonewton meter, and we convert it accordingly to the units that we're using, which is Newton and millimeter. Okay, and then this value of M is divided by FCK and B and also D square. So we get 0.132, which is less than 0.167. So therefore, we do not need compression reinforcement because K is smaller than K balance. Next, we calculate the value of the moment arm Z using the given equation. So we get Z equals to 0.87 D. And then we use the design equation for the area of tension reinforcement. Then we will get the required steel area as 2275 square millimeter. So we put the output on the right column. And then when we refer to clause 9.2.1.1 in Eurocode 2, as minimum is given by this equation there. And then for concrete characteristic strength of 30 megapascal, the concrete tensile strength is 2.9 megapascal. So when we substitute the concrete tensile strength as 2.9 megapascal in the equation, we get as minimum equals to 328 square millimeter, and is more than 0.0013 BD. So the as minimum calculated is okay. Next, we calculate the maximum area of reinforcement, which is 4% of the concrete cross section, or 0.04 BH. So it is equal to 9600 square millimeter. So we put the output on the right hand column. Based on the required steel area of 2275 square millimeter and 25 mm bars, so we see how many bars will give us the required steel area of 2275 square millimeter. So it is this value that gives us 5 numbers of 25 mm bars. So we use 5H25, meaning that we're using 5 numbers of 25 mm bars of high-use steel to give AS provided equals to 2455 square millimeter. So we put the AS provided equals to 2455 square millimeter on the output column. And then according to Eurocode 2 section 7.4, we need to check for deflection. So to check for deflection, we need the value of rho. So rho is AS required over BD. So AS required as calculated just now is 2275, and then B is 400 and D is 544 mm. So this is equal to 0.0105. And then rho 0 is square root of FCK times 10 to the power of minus 3. So square root of characteristic strength of 30 multiplied by 10 to the power of minus 3, we get 0.0055. And then in this design we do not have any compression reinforcement, so rho prime is equals to S prime, which is 0, divided by BD is also 0. And then from table 7.4n we have simply supported beam or one or two way simply supported slab with K equals to 1. So we have K equals to 1. And in this case, rho is greater than rho 0. So we use equation 7.16.b, which looks like this. So we substitute all the values of concrete characteristic strength of 30, and then rho 0 of 0.0055, rho of 0.0105, and rho prime of 0, and then the concrete characteristic strength of 30, rho prime of 0, and then rho 0 of 0.0105. So when we solve for this, we get L over D basic, which is 15.3. So after that, we look at the modification factor for span greater than 7 meter. So our beam is 7.5 meters. So we have to multiply the L over D ratio with 0.93. Okay, and then we're designing a rectangular beam, so we do not need to consider the situation where you have a T-beam. And then the next factor that we consider is modification factor for steel area provided. So we have AS provided of 2455 square millimeter, and then we have AS required of 2275 square millimeter. So this factor is 1.08 and is less than 1.5, so is okay. Then the allowable span to depth ratio will be the basic LVD ratio, which is 15.3, multiplied by the factor considering the span more than 7 meters, and then another factor considering AS provided over AS required. So we get 15.4. And then in the beam, we have the actual L over D, which is the span, which is 7.5 meter or 7,500 mm. And then the effective depth D is 544 mm. So the actual L over D ratio is 13.8. And then the allowable L over D ratio is 15.4 as we have calculated from there. Okay, so we conclude that the deflection is okay when the actual L over D ratio is smaller than the allowable L over D ratio. Next, we want to look at cracking. So for cracking, first we refer to table 7.1n to get the maximum crack width. So refer to table 7.1n to get the maximum crack width. So in our design, our beam exposure class is XC3. And then for reinforced members, we refer to this value of 0.3 mm. Therefore, Wmax is 0.3 mm, and we put the output on the right column. And then for steel stress, we use the quasi-permanent load as mentioned before. So it's permanent action plus 30% of variable action. So this is Fyk, which is the U stress of the steel. And then at the bottom here we have 1.35 GK plus 1.5 QK. And then we have another term that we consider, which is as required over as provided. Sometimes we do not consider this values as well, so it's optional. In the design guidebook, you don't have as required over as provided term, so it's okay if you do not consider this term as well. But in this particular example, I would like to consider it, right? And then for the moment redistribution consideration, we ignore it. Okay, so just substitute all the values of characteristic strength of reinforcing steel of 500 megapascal, and then GK is 16 kilonewton per meter length, and then QK is 30 kilonewton per meter length, and then 1.35 GK plus 1.5 QK as denominator there. And then we have as required of 2275 square millimeter and as provided of 2450 square millimeter. So that gives us the steel stress of 151.5 Newton per square millimeter. So for table 7.3n, with the steel stress of 151.5 Newton per square millimeter, this is less than the minimum value of 160 Newton per millimeter. So meaning that for crack width of 0.3 mm, we can use this value of 300 mm as our maximum bar spacing for crack control. So the maximum bar spacing for crack control is 300 mm. And then the actual bar spacing in our design, so we have 5 bars as one layer of arrangement, okay, and these bars are 25 mm bars. Okay, so initially we have the width of 400 mm, okay, and then we minus off the 2 nominal concrete cover, okay, and then we minus off 2 times the link diameter, okay, and then we minus off 2 times of half diameter of the main bar, okay, then we divide by the number of bars minus 1, which is the number of spacing that we have. So for 5 bars we have 4 spacing. So 5 bars we have 4 spacing. So from this calculation we get that our spacing S is equal to 72 mm and is less than the maximum distance between bars of 300 mm from table 7.3n. So the design is okay. So that's all for the explanation on the design example. Thank you very much for listening.